So we know how to arrange. We know how to figure out how many ways there are to arrange some amount of energy among some number of oscillators. The interesting thing, though, is going to be if we have two systems that are interacting, like the ice cube and the coffee, or the block of aluminum and the block of iron, or whatever, figuring out how many ways there are to arrange a certain amount of energy among the energy that one brings and the energy the other brings among both of them. How many ways there are to share the energy. So let's think about sharing energy. If we have two objects that are in contact with each other, let's see if we can just think about this for a minute. There are two objects in contact with each other. They have a total amount of energy, E1 plus E2. So E1 is some number of quanta times the amount of energy in one quantum. E2 is some number of quanta. There are 10 ways to arrange an amount of energy E1 in the first object. And there are 15 ways to arrange amount of energy E2 in the second object. How many different ways are there to arrange all the energy so that the first object has E1 and the second one has E2? Well, what do? Do you add them? Okay, so we could add, we've heard two proposals. You add them, you take the minimum. Any other proposals? Multiply them together. Let's see if we can figure it out. Well, adding has a certain simplicity. The question is it going to give us an answer that's useful? Well, all right. So let's see if we can draw a picture and see if that'll help us. So there are 10 ways to arrange the energy in this one. So here's way number 1, way number 2, number 3, number 4, number 5. Okay, so suppose we consider number 1. We've taken one of these ways of arranging this amount of energy in this object. How many possible ways are there to arrange that amount of energy in that object? There are 15 ways, aren't there? There's 1, 2, 3, 4, 15 ways. So we have 15 ways. So then we abandon this. We take way number 2 of arranging this energy. How many ways are there of arranging this energy? 15. So it looks like for every way we pick here, there's 15 ways here. So it looks like the total number of ways is omega 1, the number of ways of arranging that energy there, times omega 2. It's the product. Okay. So, given that, here's what we're going to try to calculate. We have time to do this. Suppose we have two atoms that are interacting. So we have two objects, one atom, another atom. Each atom has 3 oscillators. And we have 6 quanta of energy to put into these atoms. So we have 2 atoms, 6 quanta of energy. And we're going to figure out what the most probable arrangement of that energy is going to be. So 2 atoms, therefore 3 oscillators per atom, 6 quanta. What's the most probable arrangement? And here's how we're going to do it. We're going to make a table. We're going to say Q1 is the number of quanta of energy we're putting in atom 1. And Q2 is the number of quanta we're putting in atom 2. And then we're going to find the number of ways of arranging this amount of energy in atom 1. The number of ways of arranging that amount of energy in atom 2. And then we're going to take omega total is the product of those two. And we're going to make a histogram. A histogram, bar graph. So let's do one together, and then you guys are going to do the calculation sort of distributed. So we could start out, we have 6 quantas, so an easy thing to do would put 0 of them in atom 1 and all 6 in atom 2. Okay, so how many ways are there of arranging 0 quanta of energy in 3 oscillators? 1. Okay, that was an easy calculation. How many ways are there of arranging 6 quanta of energy in 3 oscillators? Well, we have 6 plus 3 minus 1 factorial divided by 6 factorial times 3 minus 1 factorial, which is equal to 28. And so the total is 1 times 28 equals 28. Okay, so we did 1, but now we need to calculate what happens if you put 1 and 5, or 2 and 4, or 3 and 3, or 4 and 2, or 5 and 1, or 6 and 0. Okay? So here's what we're going to do. We have 1, 2, 3, 4, 5, 6 things to calculate. So, all right. So you guys are going to do 1 and 5, this row here. And you guys are going to do 2 and 4. And you guys are going to do 3 and 3. You can't do 1. And you're going to do 4 and 2. And you're going to do 5 and 1. And you guys get to do 6 and 0. Okay? And when you've got a number, check with your neighbor, and then we'll put it in. And we're going to make a graph. So this is Q1, the number of quanta in object 1, 0, 1, 2, 3, 4. Okay, so, you might not want to do it, but I can guarantee there will be a problem related to this on the final exam. And so I think that probably it would actually be a good idea to do this problem in class, just because that makes taking the final exam so much easier. Okay, anybody got 1 and 5? What'd you? That 63 goes here. What were the number? What goes here? 21. Okay. What about 2 and 4? What? Do you? What's 5 and 1? All right. So what about 2 and 4? Who got 2 and 4? What did you get? Okay. And who got 4 and 2? Oh, okay. And 3 and 3? Who got 3 and 3? 10, what? 10 and 10. So that looks like 100. And what was 6 and 0? 28, 1, 28. Okay, so let's make our graph. And it looks like the maximum is 100. That's 50. So we've got okay. So for 0 and in number 1, we get 28. So that looks like our bar here. And for 1 in atom 1, we get 63. And for 2 in atom 1, we got 90. And 3 and 3 was 100. That looks a little high. And then it went back down to okay, so this is the number of ways of arranging the energy as a function of Q1, the number of quanta in object 1. What's the most probable arrangement? Yeah, because there's more ways of arranging it. These are not too much less probable. But we'll find that when we start computing these distributions for bigger systems, the peak gets very steep. Now, how do you think about this? It's important to talk for a minute about what this means. What this means is that suppose you have these two atoms and you take a snapshot of them every second for a year. And you just write down, when you take the snapshot, you write down how much energy is in atom 1 and how much energy is in atom 2. So you sit there, look at this system, you take the snapshot, and then you take another, and what you're going to find is that there's more times when there's 3 and 3 than anything else, but those are close. Okay, so, or another way of thinking about it is, suppose you had 100 systems, each consisting of 2 atoms, and you set them all up, and then you took a snapshot and you looked at them all simultaneously. How many of them would have 3 and 3? Well, more than any other arrangement. So we're talking about two possible ways of thinking about this, either looking at one system repeatedly over time for a long time, or having a bunch of identical systems and looking to see what fraction of them are in there. Now, the fact that this is most probable reflects an assumption that we haven't actually stated yet, but is sort of the key piece of statistical mechanics. And the piece is that the assumption is really important. It is that by itself, every way of arranging energy within a system is equally probable. So if we go back to our one atom and 2 quanta, okay, we found that we could do 2, 0, 0, or 0, 2, 0, or 0, 0, 2, or 110 or 101 or 001. Each of these ways of arranging two quanta of energy in one atom is equally probable. It's not right? I keep losing a 1, don't I? That one. There we go. Yeah. So it's called the fundamental assumption of statistical mechanics, and then it says that each way, once you've given a certain number of places to put the energy and a certain amount of energy, every way of arranging it is equally probable. And so, if you took 100 snapshots, you should find this 1/6 of the time and that 1/6 of the time, and that, so equal probabilities. And there's some vocabulary words that go with it. So one way of arranging energy is called a microstate. So here we have 6 microstates. And yes, each way of distributing energy, we'll get there in a minute, okay? So if each microstate corresponding to a given macrostate, what's a macrostate? Total amount of energy. In system 1. So what we're saying is that each of these 28 ways of arranging 6 quanta of energy in object 2 is equally probable. So 1/28 of the time we're going to find this amount of energy in object 2. Each way of arranging 5 quanta of energy in object 2 and 1 quantum of energy in object 1, each of these 5 ways is equally probable. Each of these 1 ways is equally, so each of these 21 ways is equally probable. Okay, it doesn't, but when you look at what you're going to get, so you work it out, okay, each of these ways is equally probable, but there are 21 ways to do this and 3 ways to do that. So in the end, we can get this. There's 28 ways to put 0 quanta in one and 6 in the other, but there are 100 ways to put 3 and 3. And if each of these 28 ways is equally, and each of these 100 ways is equally probable, then we're going to see 100 more. We're going to see this more than that. So sort of imagine the picture. There are just more pictures you can draw that have it that worked out that way. So that's the fundamental assumption of statistical mechanics. And that's going to be, and that and this way of counting how we distribute energy are going to be all we need to look at, to understand. That's why it's more probable that energy will flow from hotter or colder objects. We're going to be able to actually define temperature, a real definition of temperature, and we're going to be able to predict specific heat capacities. So it's going to end up being, that's it. We've got all the basics now. We're just going to do some counting.